Give me your number, I call you up. You act like you're gonna interrupt. I don't have no trouble with you fucking me, but I have a little problem with you not fucking me. Baby, you know.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. In the last example, we have yet another mass pulley system. And we would like to know the acceleration of this mass, m, as it falls down when the cable wound around the wheel unwinds. So we're looking for value of a, let's call this ay, and we have y direction, or positive y direction is directly down. The easy mistake here to make is to assume that the tension force in this spring or in this rope is same as the mass, but that is just not true. Otherwise the mass wouldn't be falling around or falling down. So we need to have free body diagrams for this, and here they come. As we see, for the block there is of course the mass mg pulling it down and the tension force that I mentioned, and it is the tension force that is accelerating the wheel. And of course the wheel has some inertia in it, so it will reduce the value of acceleration of the hanging mass. Most cases when we have drawn free body diagrams, we have only considered the forces as shown here. But in general case, we also have to consider the torques. And for that purpose, let's define a positive direction of rotation, or torque, even in a counterclockwise direction. So now we get an equation that takes into account the torque. Let's do it, or let's deal with the wheel first. So the net torque about some, let's call this axis C, again pointing towards us, is going to be the mass of inertia, or moment of inertia of the wheel times its angular acceleration, like this. And that's all we can tell from the point of view of acting forces or torques that are of interest to our problem. Of course there's the mass mg here and the support force, but they don't do anything in terms of rotation or even the movement of the body, so we'll ignore them for this calculation. Then what about the block? So within the block there are no torques acting because all the forces act in the center of the mass, but we have this linear movement or acceleration that results from the difference between these two forces. So first of all we have gravity mg pointing down, and then the tension force pulls up, and those two forces together give the linear acceleration down. So we have two unknowns, tension force T and the acceleration Y. So we have to take one of those from the equation for the cylinder. What is the net torque? It is only, or the only torque acting on the wheel is that produced by the tension force in the rope. So it turns to rotate this wheel in the positive direction, so we take it as positive. So, and its magnitude is the force times the lever arm, which is capital R, the radius of the wheel, so TR equals moment of inertia of the wheel times its angular acceleration. So now we introduced another variable, angular acceleration, when we want the linear acceleration. However, the point of contact of the rope and the wheel, that has the same linear acceleration ay as the mass, because they are connected by this tight rope. So hence we can say that the linear acceleration is the same as the angular acceleration AC times the radius of the wheel. And then we, from here, we get for alpha c, the angular acceleration to be ay divided by r. And we can plug that in here. So we get tr I times ay divided by r. And now we can solve for the tension force to be I times ay divided by r squared. And what is the moment of inertia of the wheel? So we can look it up on a table. It's half times mass of the wheel times the radius squared. So we can plug that in here for I, and we get half times mr squared ay divided by r squared. So these two cancel, and we are left with may, it's not may, divided by 2. And we'll plug the t to the equation that we have for the block. So we get mg minus may divided by 2 equals may, and we organize terms, so mg, then everything with the ay goes to the right hand side. We have m plus m over 2, and that is g, and then we can solve for the ay to be g times m divided by m plus m over 2. As usual, let's check a couple of test cases to see if this result makes sense. First of all, if we have a massive wheel so that the capital M is much larger than the small m, this effectively reduces the acceleration to a really small value, which makes sense. Heavy wheel is hard to turn, which means that the mass that is tied to the rope also accelerates slowly. On the other hand, if the mass of the wheel is really small, negligible or small compared to the mass of the block, then this term here goes to 0, and then the acceleration approaches the value of g. Hence, the block would just be in a free fall, which is what we expect.